So here we are. Before we start with any details, let me tell you about the generalized new reactions that I want you to know. And here's the circumstance. We'll start with this one. Let's say you have a reaction that's this. And not only are you going to have it in the protic solvent, acting also as the nucleophile, what we know as solvolysis, but we're also going to add lots of heat. Let's make it 150 degrees. Well, I guess we can only make it 100 if it's water. 100 degrees Celsius, it's in boiling water. Now, we did know from previous experiments, we know tertiary substrate, weak nucleophile, protic solvent, SN1. But in this case, we're heating it. And an interesting thing happens. Because we're heating it, we're going to end up with a different product. And I want you to understand the details. What we're going to end up with is the alkene. That's a double bond, badly drawn. And the reason we're going to end up with the effect of ending up with the alkene is that we're also going to end up with the water at the end, and we're going to end up with the bromide. And so two materials became three molecules. Now, this is actually a favorable reaction versus substitution. You're thinking, well, why is that? Well, let's do a little bit of almost mathematics. And that is that delta G equals delta H minus T delta S. And we want favorable reactions have a negative value for Gibbs free energy. I know you're loving this already, right? But if the temperature was low, it would be all about the enthalpy. But if the temperature is high, it starts to become about the entropy. And we've gone from 2 molecules to 3 molecules. In other words, at high temperatures, this term starts to take over versus enthalpy to create a negative delta G. So at high temperatures, I'm going to drive it from substitution. Now I've lost the bromine, and I've obviously also lost a hydrogen from here somehow. So this has become elimination. So we're losing a hydrogen, or proton, in fact, and a bromide. And in the act, creating, if you will, hydrogen bromide and water in that alkene. So at high temperature, SN1 becomes elimination. And I'm going to tell you why it's called E1. So this is an important point. When I was saying SN1, what I wasn't telling you was that E1 would happen as well. And when I talk about E1, SN1 will happen as well. The elimination and the substitution go hand in hand. So what is SN1? Well, SN1 is 2 steps. So they're both 2 steps, right? So the rate limiting step, the rate defining step, is that creation of the carbocation. That is true in either case. The question is, and it's temperature dependent typically, does it substitute in this case, water on and make the alcohol? Or does it eliminate the bromide? Or does the bromide leave and does it become an alkene? So what I'm saying is, let's look at our first simple example. Under all circumstances, if we have a weak nucleophile here, we're going to make that sp2 planar triangular carbocation. The protic solvent stabilizes that. And at 0 degrees Celsius, the predominant product is the addition of the water to make that T-butyl alcohol, tertiary butyl alcohol, if you will, 1,1-dimethyl ethanol. But another thing could happen. At high temperature, because of Gibbs and entropy, what I want you to see is that there are hydrogens on all these methyls. And what that water could do, curving arrows. Now, what it's doing is it's plucking off that proton. Plucking, by the way, is actually almost so common that it's the actual name for what you do with a proton. You pluck it off. I'm plucking off that proton. Those 2 electrons have to go somewhere. They see that carbocation. They collapse to that bond, forming a pi bond. And my other product is the alkene. So SN1, E1. And by the way, let me remind you, even though I'm saying E1, there's some SN1. And I say SN1, and there's some E1, which can, if you're doing the chemistry, drive you crazy. But I could drive it to product by heating it and getting mostly elimination. So people will tend to say SN1, E1 reactions, type reactions. And that's the first thing I want you to hear. So be aware of what we're talking about. Tertiary substrate, weak nucleophile, protic solvent, temperature dependent, SN1, E1. Now we also have an SN2. So do we have an E2? And of course, the answer is yes, of course. We also have an SN2. So why might that happen? Well, here's my primary substrate. And all I have to do is bring a strong nucleophile, strong base to it, and I'll get SN2, the one-step reaction, sodium hydroxide, which have NaOH, produce. But what if I bring some crazy bulky base? I'm going to have that potassium T-butoxide. Now, we discussed this. You can have a strong base that's a terrible nucleophile. In other words, that base can't be a nucleophile. It can't do SN2. So, but it hates being the T-butoxide. It's the conjugate base of an acid with a pKa of 16. So what does it do? It acts as a base. It's going to eliminate. Watch how it does it. That C has 2 hydrogens. Proton plucking. Oh, no, 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 no. You would expect, if you did what I just did on the exam, I'd be so disappointed. Let's go one carbon away. One carbon away. Apologies. Because what we need to do is have this collapse. So there's my negatively charged oxide, alkoxide. It's going to pluck off that proton. And those two electrons have to go somewhere. So they collapse to here. And that creates a carbon with 5 bonds. They have a good leaving group. So that leaves. It's all in one step. All of these are, after all, concerted mechanisms, meaning they all happen coincidentally, literally all at once. And I end up with the alkene. So I've used a strong base. I've done it in one step. So this is not SN2, it's E2. So there are my new mechanisms I want you to know. There's SN1 and E1. They're both 2 steps. One eliminates by plucking off a proton, the electrons collapse. In this case, oh, let me give you another E2 before I wrap up this idea. Let's say that it's the substrate that's bulky. We already said if you had a strong nucleophile, well, it can't attack from the backside. It can't do that chemistry because there's so much steric hindrance. But let's say you have a strong nucleophile. Let's have the sodium salt of methanol. So it's sodium methoxide, CH3. So that thing is a strong base, and it's not bulky, but my substrate is. It can't attack the backside, so it can't do SN2. So what can it do? Well, exactly what we just saw. You go 1 carbon away. Here's my strong base. Acting as a base, not a nucleophile in this case. Plucks off that proton. That collapses to the pi bond. The chloride leaves. We get the elimination. So, again, E2, all a concerted mechanism. So let's have a shorter video. The second video is shorter because it tells you the big ideas, which is SN1 and E1, SN2 and E2. All these 4 reactions are important. I'll come back in the next video, fill in the details of E1 and E2, and then we'll start to do some decision tree things. You get a substrate and leaving group and a nucleophile / base in a protic or aprotic solvent. Which one of these 4 will be the major product? And that's an important decision tree to go through. So thanks for your time. Welcome to Synthetic Methods. This is where it gets really exciting, where it becomes organic chemistry. So welcome to the world of synthetic methods.